Okay. Hello, everyone. Let me quickly just start uh, this event. Okay. Um, okay. Uh, there are 17 people. So, um, I'm going to wait like 2 minutes for more people to join. Um, People can hear me, right? Okay, great. So while we're waiting, um, just a quick consensus, a quick vote. Do people want me to release the solution to the problem set today or in a week? So either way, you guys can submit whenever you want. There's no deadline on submissions. Um, it's just a matter of if people want to see the solution now. Okay, so I'll release it in a week. Um, uh, let's wait till we get to like 25 people and then I'll start. Okay, whatever. I'll start now. So remember last week we talked about propositional logic. So we're going to talk a little bit more about that this week. What our main goal is to prove something called the compactness theorem, which is a very useful theorem. It pretty much says that um, it says that if I have a set of formulas x is satisfiable. So which means it has some sort of model. There's some W which satisfies X if and only if every finite subset of X is satisfiable. So obviously one direction here is trivial. This direction is trivial because if X is satisfiable, then every subset of X is satisfiable by the same valuation. And now what we want to try to prove is the converse, that if every finite subset of X is satisfiable, then X itself is satisfiable. Okay, so for this theorem, for this lecture, we're going to need the following lemma that you all should be familiar with. It's Zorn's lemma. It says that if X is a partially ordered set and H is a subset of X, such that for every chain, so for every chain in C, in H, a chain is uh, a set such that C with the partial order is linearly ordered. So for all x and y in C, either x is less than y or y is less than x. So that's what a chain is. Such that for every chain, C has an upper bound in H. So every chain has an upper bound in H. That implies that H has a maximal element, an element where no other element is bigger than it. This is equivalent to the axiom of choice, we're not going to prove that. We might discuss that later on when we get to set theory. But for now, we're going to use this lemma to prove. Uh, we're going to use it once in this lecture, but I just wanted to um, remind you all about it at the beginning. So let's begin with actual propositional logic. Um, so I wrote this in the problem set, but we're going to use the notation. If W is a valuation, phi is a formula, then W satisfies phi if and only if W of phi is equal to 1. So this is notation. This is called the satisfaction relation. And so it's a relation between valuations and formulas. And we're going to define another relation that uses the same symbol. Let X be a set of formulas and phi a formula itself. Then phi is a consequence of X, which we write as, using the same symbol, but now on the left-hand side, we have a set of formulas instead of a valuation. So we'll always know which, if we're talking about the consequence relation or the satisfaction relation, depending what's on the left-hand side. So phi is a consequence of X. If when W satisfies X, W also satisfies phi. So for example, if alpha, the set alpha beta, so a consequence of the set alpha and beta is alpha conjunction with beta. Because if W satisfies alpha and W also satisfies beta, it must satisfy the conjunction. A nice thing to note about the satisfaction relation is W satisfies alpha and beta if and only if W satisfies alpha and W satisfies beta. Similarly, for alpha disjunction with beta, if it satisfies one of them, and W satisfies the negation of alpha if and only if W does not satisfy alpha. So that's some quick notes about the satisfaction relation. So we could actually have defined the satisfaction relation recursively without talking about valuations. We could have without extending it to a function on formulas, we could have just defined it as a relation using this recursive method. But that's not important. And okay, so that's the consequence relation. I'm going to use the convention that if I have a finite set, I write instead of writing the set phi 1 through phi n satisfies phi, I'm going to write just without the curly braces. And similarly, I'm going to write x alpha, so phi is a consequence of x and alpha, to mean x union with alpha satisfies phi. So these are just some conventions. One more definition. Phi is a tautology if the empty set if it's a consequence of the empty set. So this is equivalent to saying to W satisfies phi for all valuations W. So if everything satisfies phi, then phi is a tautology. Tautology. I think that was in the homework. I think we defined this already, actually, but doesn't really matter. Phi is a contradiction if the negation of phi is a tautology. equivalently, W does not satisfy phi for any W. Okay. So for example, alpha or the negation of alpha, alpha implies alpha, and alpha if and only if alpha are all tautologies. And alpha and not alpha, alpha implies not alpha, and alpha if and only if not alpha are all contradictions. Sorry, not this one. Okay. Okay. And so now we're going to note some important properties of the consequence relation that we're going to generalize later. Firstly, it's reflexive. So alpha is always a consequence of alpha. So this is reflexivity. If alpha is a consequence of x, and x is a subset of x tag, then it's also consequence of x tag. So this is monophonicity. And if y is a consequence of x, and alpha is a consequence of y, then alpha is a consequence of x. This is called transitivity. So this here means that every phi in y is a consequence of x, right? So that's a pretty natural sort of extension. Okay, so we have these three properties of the consequence relation, and we can actually add a fourth, which is going to be on the problem set, and that's another way, using that fourth property, it's another way of proving compactness. But right now we're going to ignore that. And another interesting property that for the consequence relation is the deduction theorem. It says that x, so alpha implies beta, is a consequence of x if and only if if beta is a consequence of x and alpha. And this should be like a pretty natural thing, because if I want to prove that alpha implies beta, given some axioms x, I'm going to assume the axioms and x. I'm going to assume the axioms x and alpha, and from that I'm going to prove beta. So this is a pretty natural thing, and we can see that it's pretty trivial to prove. So in one direction, if W satisfies x and alpha, then since W satisfies x, W must satisfy alpha implies beta. So W satisfies beta, because we know that it also satisfies alpha, and it satisfies alpha, and it satisfies alpha implies beta, so it must satisfy beta. And conversely, if W satisfies x, if W satisfies alpha, then W satisfies x and alpha, so W satisfies beta. And so basically what we have here is if W satisfies alpha, then W satisfies beta, which means W satisfies alpha implies beta. So we have both directions here. It's a quick proof. So don't, but it can be, what's nice is that when you're talking about other consequence relations, so we're going to generalize this notion of consequence relation in the problem set, but a lot of times for specific consequence relations, you want to prove the deduction theorem for them. Hi, Ricey. And the deduction theorem is just it's when you want to prove things about implication, it's very useful. But anyway, let's now get to the bulk of our uh, of our lecture. And so what we're going to do is we're going to prove the compactness theorem by proving what's called uh, finitariness of the consequence relation, which says that alpha is a consequence of x if and only if it's a consequence of x naught for some finite x naught, which is a subset of x. So obviously one direction here again is trivial. If it's this direction, right? If it's a consequence of some subset of x, and it's a consequence of x itself by the monotonicity uh, property. But the other direction is hard. So we're going to actually prove this in a sort of roundabout way. We're going to define what's called a Gensen calculus. Okay. A Gensen calculus is a relation. It's a relation between sets of formulas and formulas. So in other words, it's a subset of PF times F. Oh, and an important note, in this section, we're just going to take the functional complete signature with conjunction and negation. And we're not losing any generality here because it's functional complete. Okay, so it's this. Okay, so Gensen calculus is a relation between sets of formulas and formulas, with a set of basic rules of the form. So we have a bunch of rules of the form if alpha 1 is a consequence of x1 through alpha n is a consequence of xn, then alpha is a consequence of x. So all of our rules are going to look like this. And so basically what it says is that if alpha I is a consequence of xi for I equals 1 through n, then alpha is a consequence of x. So for example, our Gensen calculus will have the rules, have the following 6 rules. So these are going to be our rules that we're going to use for our Gensen calculus. We're going to have the initial sequent rule, which has no premises. Oh, so this stuff at top, these are called premises. And this is our result or conclusion. Gensen calculi, so this is not the most natural way of, so what I'm doing here is I'm defining really what it means to prove something. And this is not the most natural way of doing it. I'll get to that later. Well, in my opinion, it's not the most natural way of doing it, but it is very useful in that proving what we want to prove is very easy with Gensen calculi. And also, they have applications in computer science. So if you want to do type inference, for example, that uses Gensen calculi. But I digress. So first we have the initial sequent rule. Then we're going to have the monotonicity rule. So if alpha is a consequence of x, then it's also a consequence of x tag for x tag, x prime, sorry, which is a superset of x. So that's the monotonicity rule. Now we have conjunction 1. It says that if alpha and beta are both consequences of x, then alpha conjunction with beta is also a consequence of x. Similarly, we have the converse. If alpha and beta is a consequence of x, then both alpha and beta are consequences of x. So this is N2. And our final two rules are if both alpha and the negation of alpha are consequences of x, then every beta is a consequence of x. So basically what it means is if x is inconsistent, you can prove anything from x. So far, everything that I've written here holds for our consequence relation as well, right? Like I can switch this single line consequence relation with our double line consequence relation, and everything here, like it would be true. And finally, we have the last one. So if x and alpha prove beta, and x and the negation of alpha proves beta, then x itself proves beta. We don't need alpha. And this is negation 2. So these are our 6 rules. All of these are true for our previous consequence relation. So we can say that our consequence relation satisfies all these basic rules of against in calculus. What is a proof going to look like for against in calculus? So call rules without premises axioms. A derivation is a sequence of sequence. So a sequent is just a pair x and alpha, so x proves alpha. No, so the homework is for the first lecture. I'm going to be giving another problem set for this lecture. Okay, so it's a sequence of sequence. S1, S2 through Sn, where Si is an axiom or can be obtained from S1 through Si minus 1 using the basic rules of the calculus. So let's give an example. So here's an example. We want to prove that alpha and beta prove that alpha conjunction with beta, right? What we had before. Now what we're going to do is we're going to start with the initial sequent rule. So we start with that, and then from that we use the monotonicity rule, and we have that alpha and beta prove alpha. And then we're going to do the same thing, but now with beta. So we start with the initial sequent. Now alpha and beta prove beta as well. And finally, we're going to use, now we have these two sequence, and we're going to use conjunction 1, and we get alpha and beta proves alpha and beta. So just a reminder, conjunction 1 just says that if x proves alpha and x also proves beta, then x proves their conjunction, which is exactly what we have here. So we've proven using our Gensen calculus that if alpha conjunction with beta is a consequence of alpha and beta. Okay. Some more ones. I'm going to prove some more rules. Let's prove cut elimination. Oh no, sorry. Negation elimination, which is if x and the negation of alpha prove alpha, then x proves alpha. So we're going to start with x and alpha prove alpha. This is by the initial sequence and monotonicity rule. Now, we also know that x and the negation of alpha prove alpha by supposition. And 3, we can use negation 2 to get that x proves alpha, right? Because we have x and alpha proves alpha, and x and the negation of alpha proves alpha. So the proof, in a way, doesn't depend on alpha or the negation of alpha. X just proves alpha. Okay, so that's cut elimination. 2, we have reductio ad absurdum. I think that's how you pronounce it. But anyway, it pretty much says that if x and the negation of alpha proves beta and the negation of beta, then x proves alpha. So if basically it says that if we assume the negation of alpha and we get a contradiction, then x proves alpha. It's sort of like a proof by contradiction. 1, so we're going to have x and the negation of alpha prove beta and the negation of beta. This is by supposition. 2, x and the negation of alpha then proves alpha by the negation 1, by negation 1, that rule. And 3, we have by negation elimination, we get x proves alpha. So here we've used a previous result to prove another result. Okay, so here technically this is not our proof does not. Okay, firstly our proof doesn't use 3 steps, because we've kind of so our proof doesn't use 3 steps because we're sort of taking this proof here and inserting it here, but it doesn't really matter. So we've proven this. And our third one, let's prove the cut rule. If x proves alpha and x and alpha proves beta, then x proves beta. Okay, so so x and the negation of alpha proves alpha by supposition. 2, x and the negation of alpha proves negation of alpha by initial sequence and monotonicity rule. Oh, this one's also monotonicity rule. 3, by the by negation 1, we have that x and the negation of alpha proves beta by negation 1. Okay, and now we also have 4, we have x and alpha proves beta by supposition. And then 5, we just get x proves beta by negation 2. Right, so these two together by negation 2, we get x proves beta. So I prefer if you didn't use theorems from this lecture to prove the problem set from the previous lecture, because you're not supposed to need to, but if you want to, you can. I don't really care. Okay, so I'm not going to formalize this. If you guys want to formalize it, you can look at actually, no, let's formalize it. Okay, so let E be a property of sequence. So that means I write E x proves alpha to mean that it holds for the sequence. It is closed under the rule x1 proves alpha 1, xn proves alpha n, x proves alpha if E x1 proves alpha 1 through E xn proves alpha n implies e x proves alpha. So for example, if I wanted to say that some property of sequence holds for negation for and 1, I would say if e x proves a and e x proves b, then e x proves their conjunction. So that is being closed under this rule here. So pretty much now what I'm going to say is that if oh and one so our lemma of induction is just going to say if E is closed under initial sequent through negation 2, then if X proves alpha, E of the property holds for that sequent. So the proof is induction on the length of the derivation of X proves alpha. And I will leave that for you guys to read from the lecture notes. It's not a very enlightening proof. So for example, let's do lemma, let's prove the soundness of this of our Gensen calculus. Pretty much if X proves alpha, then alpha is a consequence of alpha. Then alpha is a consequence of X. So we're going to prove this by induction. We're going to define E of the sequent to mean X alpha is a consequence of X. And then all you need to show is that it's closed under all these rules. So firstly, for the premiseless rule of the initial sequent, we need to show E of alpha of this sequent of alpha alpha. Because it has no premises, this here is always true. It's vacuously true. So we need to show the E of the result. And obviously, we need to show that this is true since alpha is always a consequence of alpha. And 2, it's just similar things. We can obviously see that all of these are closed under our property, right? If alpha is a consequence of X and beta is a consequence of X, then alpha conjunction with beta is a consequence of X, and so on. The more interesting result, well, this is obviously a very important result, but the more interesting result that we're going to end up using is finiteness. If X proves alpha, if X proves alpha, then X naught proves alpha for some finite X naught. So the proof here is by induction. I'm just going to define X, this property, to mean that X naught proves alpha for some finite X naught. So that's our property. And for the initial sequent, this is obviously true. E of alpha is a consequence of alpha proves alpha. This is obviously true because we can just take X naught to equal the set alpha, and this is finite. 2, for the monotonicity rule, if X proves alpha and X prime proves alpha for X prime is a superset of X, then because by induction E of x alpha, so x naught proves alpha for x naught subset of x, finite. And so x naught is also a subset of x prime. And we have what we want. These are both very simple. The other results are simple. I've just proved this for this rule. If x proves alpha and beta, then it proves their conjunction. So we need to show that E of x proves alpha and E of x proves beta implies E of x proves alpha and beta. So for here we have some x naught, let's call this x1, which is a subset of x, x2, which is a subset of x. This one proves alpha, this one proves beta. Then if we define x naught to be their union, we have x naught proves alpha and x naught proves beta by monotonicity. And then we know that x naught proves alpha and beta, and x naught is going to be finite. So we have what we want, and you just do the same thing for the rest of the rules, and you get this result, that if x proves alpha, then some finite x naught proves alpha as well. Okay. So firstly, Gödel's incompleteness theorems are that's kind of up for us to choose later on. I think Sharp said he wants to at least talk about them. I don't find their proofs very interesting because they're not model theoretic. This lecture series has a focus on model theory, not proof theory. So we're not going to focus on that as much, but we might talk about it. And okay, so what we're doing here is I must have forgotten to say, but our goal is to prove that our Gensen calculus is equal to the consequence relation. So right now, there is a difference between them in that they're defined differently, but the whole idea is to prove that they're equal. And implication is just that's something part of a logical signature. So it's very different from, right? If I say alpha implies beta, that doesn't mean anything unless I put some sort of consequence relation before it. Yes, both of the consequence relations. So the Gensen calculus and the consequence relation are both meta-theoretical sort of ideas, and implication is something that exists within the scope of the logic itself. Okay. Okay, one more. Our last definition. No, not our last definition. Yes, our last definition. Sorry. So our last definition is a set of formulas is inconsistent with respect to our Gensen calculus if x proves alpha for all alpha. And otherwise, x is consistent. Now, what we're going to focus on is something called maximal consistency. So, okay, so rules of inference. So rules of inference relate to so remember how I was saying that the Gensen calculus is not necessarily the most natural way of defining a proof. So in my opinion, Hilbert calculi are, and Hilbert calculi, that's where rules of inference come from. So we'll talk about that at the end, and that's also going to be on the problem set. So you guys can explore that in your own time. Okay, so X is maximally consistent if it is consistent, and if x prime is a proper extension of x prime is inconsistent. So it's maximally consistent if it's literally consistent and maximally so. So a few things to note. One is that x is inconsistent if and only if x proves a contradiction. So obviously this direction is trivial because if it's inconsistent, it proves everything. And the other direction is x proves pi and the negation of pi. So by n2, x proves pi, and x proves the negation of pi. So by negation 1, x proves alpha. Okay, so it's inconsistent if and only if. So we can boil down inconsistency to x proving a single formula. Okay, and 2, if x is consistent, it is maximally consistent if and only if for all formulas, either alpha is an x or the negation of alpha is an x. So this direction is trivial because if every formula is either an x or its negation is an x, then I can't extend x any further because then I will have alpha and its. So if because if I add another formula to x, then if that formula was not already in x, its negation would have been in x. So now I have alpha and its negation in x, and then from negation 1, I would have that x proves every formula. Yes, it is. It's a complete theory. So it's another way of saying that a theory is complete. Literally because of this point. But we're not really talking about complete theories, because propositional logic isn't really rich enough to really care about them, except for in this proof. And the other direction is if alpha and the negation of alpha is not an x. So if they're both not an x, then and x is maximal, then that means that x and alpha must be inconsistent, and x and the negation of alpha must be inconsistent. So by negation 2, this means that x is inconsistent, which is a contradiction. So if x is consistent, it's maximally so if and only if every formula or its negation is in x. Okay. Now we're going to actually start proving the completeness theorem. So our completeness theorem is exactly this. This is the completeness theorem. Is that the Gensen calculus is equal to the consequence relation. So let's begin by proving a lemma. Our Gensen calculus has the properties. So we'll call these properties C plus. So x proves alpha if and only if x and the negation of alpha is inconsistent, and C minus, where x proves the negation of alpha if and only if x and alpha is inconsistent. So the reason we need both of these properties, why one property doesn't really prove doesn't imply the other, is because our Gensen calculus is syntactic. It's not semantic. So when I say that x proves the negation of alpha, so C plus would say that x proves the negation of alpha if and only if x and the double negation of alpha is inconsistent. But then I would need to somehow get from this to saying that x and alpha is inconsistent. And so you could do that. It's just it's not trivial because uh, um, elementary equivalence is a semantic thing, and we're talking about syntactic things. Okay, so we're just going to prove C+. C minus is proved in a totally analogous way. So suppose x proves alpha, then x and the negation of alpha proves negation of alpha by initial sequence and monotonicity rule, and x and the negation of alpha proves alpha by supposition and the monotonicity rule, which means that x is inconsistent. Sorry, x and the negation of alpha is inconsistent. And now suppose x and the negation of alpha is inconsistent. So then x and the negation of alpha proves alpha. Because it's inconsistent, it proves everything. And then by negation elimination, x proves alpha. So we have both directions. So we've proven C+. Okay. Now we're going to get to our first named lemma. So lemma, this is due to Lindenbaum. Every consistent x can be extended to a maximally consistent x tag, x prime. So if I have x, which is consistent, I can take it and extend it to x prime, which is maximally consistent. Okay, so the idea is let's just define h to be equal to all the x primes, which are extensions of x, where x prime is consistent. Okay, so h, all we want to do right now is prove that h has a maximal element. If h has a maximal element, then that it's consistent and it's an extension of x and it's maximal. So we have exactly what we want. So how do we prove that a set has a maximal element? We prove that h has a maximal element by Zorn's lemma. So let C be a subset, be a chain in A, be a chain in H. We want to prove that it has an upper bound. So define Y to be the union of C. We claim Y is an upper bound for C in H. So obviously Y is an upper bound for C. What we need to do is that what remains to be shown is that it's in H. So we need to show that Y is consistent. So suppose Y is inconsistent. So that is Y proves this contradiction. By finiteness, there exist phi1 through phi n in Y such that phi1 through phi n proves the contradiction. Um, so phi I is in Ci, which is in our chain C, right? Because Y is the union of the chain, so every element in Y has to be in some member of the chain. So phi I is in Ci. Thank you. So let's just define C naught to be the maximal element of C1 through Cn. Why does this maximal element exist? Because C is a chain. So every Ci is contained in some other, so C1 might be contained in C2, which might be contained in C4, which might be contained in C3, and so on. But there is a maximum element. So phi 1 through phi n is in C naught. Thus, by the monotonicity rule, C naught is inconsistent. But C naught is an H, so it must be consistent. So that's a contradiction, and we have proven what we want to prove. So Y is an upper bound for C, and so every chain has an upper bound in H, and that means H has a maximal element, and that maximal element is exactly a maximally consistent extension of X. So it's a very simple proof. Okay. Now our final lemma. If X is maximally consistent, it is satisfiable. So there is some valuation which satisfies X. Yes, that's true. Lindenbaum's original proof does not use the axiom of choice. But in this series, unless we want to prove something doesn't rely on the axiom of choice, which doesn't really matter here, we're just going to assume the axiom of choice. Also, the axiom of choice is really neat. Okay. Define. So what we're going to do is we're going to construct our valuation W as follows. So W will satisfy P if and only if P is in X. So now we claim W satisfies alpha if and only if alpha is in X. If we prove this, then we've automatically proven that W is a model of X, right, by this direction, right? If alpha is in X, then W satisfies alpha. So all that remains is to prove this this point. We do it by induction on alpha. One for alpha prime. This is by definition, right? Because we define W to satisfy P prime, if and only if P is an X. 2 for so for alpha, if for conjunctions, W satisfies alpha and beta, if and only if W satisfies alpha and W satisfies beta, which is if and only if alpha is an X and beta is an X. And this would then imply that alpha and beta is an X, because otherwise the negation of alpha and beta is an X. And this would show that X is inconsistent, because alpha is an X and beta is an X. So X proves alpha and X proves beta. So X proves alpha and beta. So alpha and beta is in X, because otherwise the negation of alpha and beta is in X, and so X proves the negation of alpha and beta. It also proves alpha and beta, so X is inconsistent. So just a thing to note, I guess I should have noted before, if X is maximally consistent, X proves alpha if and only if alpha is in X. So it's the same thing. And we just showed that X proves alpha and beta, so alpha and beta is in X. And then 3 for the negation, W proves the negation of alpha if and only if W does not satisfy alpha, which is if and only if alpha is not in X, which is if and only if, because X is maximally consistent, it must then contain the negation of X, of alpha. So we have what we want, and that concludes our lemma. So we have we've constructed a model of our X, and we finally get to the completeness theorem. Which just says that our Gensen calculus is equal to the consequence relation, i.e. X proves alpha if and only if alpha is a consequence of X. So we've already proven that if X proves alpha, then alpha is a consequence of X. This is by soundness. We proved this earlier, all the way up here. Okay, and now we want to prove the other way. So we proved this direction, now we want to prove the converse. Suppose then X does not prove alpha, then by C plus, X and the negation of alpha is consistent. Right, because we showed C plus says that X proves alpha if and only if X and negation of alpha is inconsistent. So if it doesn't prove alpha, then X and the negation is consistent. So X and the negation of alpha is consistent. By Lindenbaum, it has a maximally consistent extension Y, which is satisfiable. So there's some W which satisfies Y, and that means that W satisfies X and the negation of alpha. That means that alpha is not a consequence of X. Because if alpha were a consequence of X, then W, because it satisfies X, it would also have to satisfy alpha. But it satisfies the negation of alpha. So we have that if X does not prove alpha, it does not satisfy. Alpha is not a consequence of X. So we've proven in both directions. So that's the completeness. And then because these two relations are equal, we get the following. We get finiteness. This is immediate. X proves alpha if and only if X naught proves alpha for some finite X naught. The proof is immediate. And our last theorem, which I promised at the beginning, is compactness. X is satisfiable if and only if x naught is satisfiable for every finite x naught. So the proof is very simple. If x is satisfiable, then every finite x is every subset of x is also satisfiable by the same valuation that satisfies x. Now the converse is if x is not x is not satisfiable. So if x isn't satisfiable, then a consequence of x is contradiction, because everything that satisfies x satisfies the contradiction, because nothing satisfies x. So this is true vacuously. This means that by finiteness, some x naught the negation is the contradiction is a consequence of some finite x naught. So if x isn't satisfiable, that implies that there exists x naught finite which isn't satisfiable. So note here that, right, again, because these two relations are equal, satisfaction and consistency are the same thing. Okay, so we've proven the compactness theorem. Now we're going to use this, now for the last part of the lecture, we're going to use this compactness theorem to prove a result that has no, that's not related to logic. Okay. Application of compactness. And there's going to be another application in the problem set. Okay. An infinite rooted tree. So an infinite rooted tree is a triple. So V, triangle, and R, where V is a set of vertices, so it's just a set of symbols, set of something. Triangle is an irreflexive relation on V. So irreflexive means that we don't have that A is in the relationship with itself. And R is an element in V such that, one, V is infinite, right, because I said an infinite rooted tree, and two, for every vertex in V, there is a single path from R to A. So a path is something, R is equal to V0, which is then a predecessor of V1, and so on until Vn, which is equal to A. So that's an infinite rooted tree. And so now our lemma by Koenig is if V triangle R is an infinite rooted tree with arbitrarily long finite paths, it has an infinite path. So this is a very interesting lemma, and it's actually a lemma that's very close to my heart because I had an interview for something, and one of the questions, it was a math interview, and one of the questions I was able to solve with exactly this lemma, which is why I'm using it in this lecture as opposed to a different application. Anyway, so So what we're going to do is we're going to first define the layers of V. So we do this, we're going to define the layers of V. So suppose that our tree looks like this. So we have R, then R has these children. Oh, sorry, one more thing. 1, 2, 3. Every vertex has a finite number of children. So what that means is that if I have this tree here, this node, for example, can't have an infinite number of children. It can only have finitely many. Okay. So let's say this is our tree. So our first level, for our first layer is just going to be the root. The second layer is going to be these three. The fourth layer, the third layer is going to be these, and so on. And that's going to be the layers of our tree. And so we define this recursively. So S0 is going to just be R. Then sk plus 1 is going to be equal to A in V such that it is a successor of it's a child of some B for D in Sk. That's it. Equivalently, this is just equal to all the children of B for B in Sk. So an important thing to note about all these SKs, all these layers, is that they're all finite. Because recursively, inductively, Sk is finite, and for every B in Sk, the amount of children of B is finite, so it's a finite union of finite sets, which itself is finite. That's an important note, because now what we're going to do, okay, first, for every A in V, define a propositional variable, P sub A. So we're going to have an infinite number of propositional variables. It could be uncountably infinite too. There's no limitation on the number of variables here. So for every, okay, now we define a set of formulas X as follows. So X is going to have three types of formulas, and these are going to tell us how to form a path, an infinite path in X, in V. So for each K, basically the idea of P sub A is going to tell us that A is in our path. And if we know in each layer what element is in our path, we can form the path through the tree. So for A in Sk, PA. Since every layer must contribute it must contribute a vertex to the path. 2, for each K and A and B in Sk, you cannot have that the layer contributes two vertices, right? I can't have a path, right? So this tree it's a directed tree. So I can't have that it contributes A and it also somehow contributes B. But I can't go somehow from here and all somehow get to here, right? Because it's a directed tree. I can't go up the root and down here. And 3, if A is if B is a child of A, then PB implies PA. The idea here is if I have my tree, and right B is in the path, then it has a single success. It has a single parent because we know that there's only one path from the root to the vertex. So it has a single parent, and that parent must also be in the path. So right, if this is B, this is A. If B is in the path, If B is in the path, that implies that A must be in the path. Okay, so these are our three types of formulas. And together, we put them together, and we get X. Now I'm going to make two claims. Firstly, that X is satisfiable. And secondly, that if X is satisfiable, then we can form a path, an infinite path through V. So first I'm going to prove that if X is satisfiable, then we can form an infinite path. So suppose W satisfies X. Then define a path. So R is equal to V0, or we don't, so it's a path V0, V1, V2, and so on, Vn, and so on infinitely. Where Vi is, so Vk is in the kth layer such that W satisfies P sub Vk. Right? We know that in each layer there's at least one vertex which is satisfied by W because of 1. And we also know by 2 that this vertex is unique. So this defines our path. Now we need to show that it actually is a path. We've just defined a bunch of vertices. We need to show that it is a path. So we need to show that Vk is a parent of Vk plus 1. But we know, so W satisfies P sub Vk plus 1, and it also satisfies X. So that means that W satisfies Pk plus 1, Pvk plus 1 implies Pvk, because Vk is the parent of Vk plus 1. So that means W satisfies Pvk. So that means, oh, sorry, I kind of did this in a roundabout way. My bad. So if W satisfies Pvk, and so we know that this Vk, wait, sorry. Let me do this in a more clear way. If A is the parent of Vk plus 1, then we must have that W, that Vk, P sub Vk plus 1 implies Pa, which means that W satisfies P sub A. Thus, and since A is in Sk, why is A in Sk, in the kth layer? Because it has to be in some layer, right? Because there's a path to Vk plus 1, it must go through A. And because there's a single path, it must be in the kth layer. It can't be in some other layer. Okay, so A is in the kth layer, and this Vk and Vk is unique in that Pvk is satisfied. So A is equal to Vk. So what we've shown is that if A is a parent of Vk plus 1, A is equal to Vk. So we've shown exactly that. We've shown that this is a path. Now what we need to show is that X is satisfiable. X is satisfiable because it is finitely satisfiable. Why is it finitely satisfiable? Because if I take a finite subset of X, we can look at all the P, so let's say I have X naught. I can look at all the vertices A such that P sub A is in X naught. And then what I can do is I can look at, let's say, Sk such that Sk and X naught have a non-empty intersection. So all the layers which have some node, some vertex in X naught. This is going to be finite still because this is finite, because X naught is finite. So this is finite, which means that this is finite. So that means that if I define V prime to be the union of all these layers, let's call this L, the union of L, V prime is going to be finite. And it also has to contain R. So there is a finite path in V prime. And this is precisely what these three formulas tell us about X naught. So we can look at the path that's the path that is in V prime, this arbitrarily long path, because it's given to us that there are arbitrarily long paths. So we can look at this arbitrarily long path, and if we take this path V0 to Vn, which is all in V prime, and define W satisfies P Vi, right? If W satisfies all these things, and for any other node it doesn't satisfy them. W does not satisfy PA if A doesn't equal Vi. Then this W satisfies X naught. And we're good. So that was a lot of words, but the idea here should be a little clearer. If there are any questions, you can ask them. But we've proven this lemma, which is a graph theory lemma, using propositional logic, which I think is very cool. And there's an even cooler, it's unfortunate, but there's an even cooler application of the compactness theorem to something called ultrafilters. The issue is I want to say that for later on in the series. So I'm not going to use that example yet. But now I want to go on a little tangent about Hilbert calculi. I'm not going to prove anything, I'm just going to define stuff. So Hilbert calculi, this is a more natural method of defining what a proof is, in my mind, as opposed to Gensen calculi. So a Hilbert calculus is a relation. So it's a relation, it's a consequence relation as well, right? I'm using the same symbol here. As well as, so, right, our calculi, it's a relation equipped with, so our Gensen calculus was a relation equipped with rules. This one is going to be a relation equipped with axioms. So, which are just a set of formulas, lambda, and two rules of inference. These are relations, a set of relations gamma, where R in gamma is a relation between between n formulas and, oh, sorry, I need to fix that in the notes, but between n formulas and a formula. So I'm going to write R phi1 through phi n implies phi. This is going to be my notation for rule of inference. So one very common rule of inference is the rule of inference of modest ponens. So modest ponens, which just says that R of alpha and alpha implies beta gives us beta. So that's a rule of inference. And a proof is a sequence of formulas phi1 through phi n such that for all I, either 1, phi I is an axiom, or 2, there exists a rule of inference, R in gamma, and phi I1, phi IN for I1, IN. So we have less than I. So if I'm looking at my sequence of phi 1, phi I minus 1, and phi I, and so on, I can look at these rules, these formulas before it, and there's a rule of inference that says phi 1, phi I1 through phi IN implies phi I. So I can take, look at the formulas before it, and these formulas using a rule of inference imply phi I. So I think this is a very natural, if you think about it for a little bit, it's a very natural way of defining proof. And this is sort of how we do proofs in general. Obviously, we don't start from axioms. We start from other results that we have, but you can sort of see how um, you can formalize a proof using this. And this is actually, for whoever was asking about Gödel's incompleteness theorem, he uses Hilbert calculi to prove it. So this is our Gensen, our Hilbert calculus that we're going to use is going to use a single rule of inference. So it's going to use modus ponens and also the following axioms. So lambda 1, which is alpha, so it's going to be over the signature of implication and negation. So alpha implies beta implies gamma, implies alpha implies beta, implies gamma. You can verify yourself that this is, implies alpha implies gamma. Number 2, you can verify yourself that this is valid. Alpha implies beta implies alpha and beta. Number 3, alpha and beta implies alpha. Number 4, alpha implies a negation of beta implies implies a negation of alpha. So these are our 4 axioms. Well, it's really this is an axiom schema. And it's really what it is for every, it's not a set of 4 formulas. It's a set of infinitely many formulas, but of this form. And then if you look at the lecture notes, I give an outline of how you can prove that the completeness theorem. So Hilbert completeness, which is just the same as Gensen completeness, which just says that our Hilbert calculus is the same as a consequence relation. And there's an outline of that proof. Okay, that's it for the lecture now. If I recall correctly, we said that we want to we want to release the solution to the problem set next week. I am still going to release the problem set for this week today. I'm going to fix up the lecture notes a little bit, if I can remember where I had issues, and then I will publish them, and I'll also publish this recording. If there are any questions, now's the time to ask. And thank you all, of course, for coming. Of course. No, it's really my pleasure. I enjoy doing this very much. And thank you, Valley. Oh, and for this problem set, there's like at the last page has a collection of hints. I put them separately so you don't need to use them if you don't want to. Like you don't need to look at them. Oh, oh, yes, of course. I wanted to make a mention. So there's also going to be, you may have seen, I made an announcement about an abstract algebra series. Um, the it's going to be starting this Thursday, and for anyone that doesn't have a background in abstract algebra, so at least doesn't know what a group is at all, or doesn't know what a ring is, um, I would highly recommend at least learning abstract algebra somehow. So I'm going to obviously recommend my series. Um, it starts this Thursday at 6 o'clock UTC PM. Um, and we're not going to be really following a single book. We're kind of going to be using Dummett and Foot. Who? I don't know how to pronounce. I don't know how to pronounce these guys' names. Um, but we're also going to be using some lecture notes that I have from my um, what's it called? From my own course in group theory and some other people's notes in group theory. Um, but we might also be using other books as well. Nice. Yeah, I've heard good things about it. I personally didn't use it to learn anything, but I've heard good things about the book. Let me stop the recording.